Spiral mill pipe operation begins at the coil preparation station. After the coil has been twice measured and again reviewed for applicability to the customer's pipe order, it's guided into the coil preparation station by means of a 54-ton overhead crane. This crane capacity far exceeds the current coil weight production of the steel industry and is designed to take full advantage of the next generation of steel coil production. The benefits of larger coils is longer production runs without interruption and more pipe having the same coil identity and rolling properties. In this case, our customers, the steel mill, and STUP are all beneficiaries. At coil preparation, the leading end of the coil is precisely cut to provide an edge that can be effectively joined with the trailing end of the coil being processed before it, which optimizes productivity. The operator at the strip feed-in station records all coil information and performs dimensional checks as each coil is unwound. Edge sensing devices ensure the coil's center orientation as the coil is guided into position for optimal alignment. The trailing end of the preceding coil and the front end of the coil being introduced into the operation are aligned and joined by welding to form a continuous ribbon of steel coil for further processing. As required, ultrasonic UT inspection of the scalp surface is performed at the station, where approximately 50% of the coil surface is evaluated for acceptance to Level B of ASTM A578. The UT system is equipped with an automatic alarm system, which includes audible, visual, and spray marking alerts, as well as an analog display of signals. Also at this station, 6 carbide alloy heads mill the strip edges to provide a clean and precise profile for presentation to the welder. The edge milling process also provides the exact coil width required for optimal spiral forming. The edge milled coil is introduced into the 3-roll edge pre-bending assembly and then into the forming assembly, which consists of 3 forming roll banks and several outside cage rolls. This forming assembly combines the strength and precision to form the exact outside diameter and the other dimensional properties of the desired pipe for tack welding at a rate of up to 40 feet per minute. This operation provides a continuous weld seam that is strong enough to keep the desired pipe OD and shape and, along with the forming technique, eliminates the potential for systemic ovality after welding. The spiral welding process provides superior straightness when compared to other processes. The application of a tack weld during forming sets the stage for superior final weld quality versus a single-stage spiral process in which the final weld is applied at the forming assembly under conditions in which the edges of the strip are in motion relative to each other. The precisely spiral-formed pipe feeds into the plasma cutoff station. As the pipe passes through the unit and approaches its final length, the cutoff unit begins to travel at the same speed parallel to the longitudinal axis of the pipe. At the same time, the unit's plasma cutting torch is rotated at the precise cutting speed required for optimal pipe end quality for further processing. Upon completion of the cutting, the pipe is assigned a pipe identification number, which includes the STUP job number, steel coil number, and the manufacturing sequence of the pipe within the coil footage. From this point in the spiral pipe manufacturing process, the pipe is moved as an individual piece throughout the remainder of the manufacturing process and continues to be handled very carefully on urethane rolls, which eliminate the risk of hard surface contact impacting the pipe surface. To prepare the ID of the formed pipe for final welding, cleaning of the interior of the pipe is done using a rotating wire brush and vacuuming unit. In preparation for final welding, an end tab plate is welded onto each end of the tack welded pipe's ID. This tab serves as the starting and ending points for the final welding operation, thereby ensuring weld arc stability and consequently consistent weld quality through the entire length of the weld, including the pipe ends. After tab plate welding, the carefully formed and prepared pipe is presented to the finish welding station, where the full length of the tack welded seam is precision submerged arc welded to completion and is qualified through a ration of destructive testing according to API and ASME Section 9 in order to confirm the serviceability of the STUP product. This operation totally consumes the tack weld and is accomplished using 3 internal and 2 external welding torches. The 3-wire ID pipe welding heads are positioned near the bottom of the inside of the pipe, while the 2-wire OD pipe welding heads are near the top of the outside of the pipe. The 2 welding locations are separated by a distance equal to about 1/2 of the spiral wrap length. Superior submerged arc weld quality is achieved, first, by precise tracking of the weld seam in order to maintain the alignment of the ID and OD welds, second, by careful real-time electronic tracking of the weld parameters, and finally by precisely automated conveyance of the pipe under the welding heads. In addition, welding at this final welding station is far more stable and results in a pipe with much more consistent weld quality than a single-stage process which has the final submerged arc welds applied during forming when the scalp edges are still in motion relative to. During the hydrostatic testing procedure, the pipe is filled with water and subjected to the specified pressure for a minimum of 10 seconds. The testing is accomplished in a 5,000 psi ultra-modern 80-foot-long testing unit and is performed to ensure that the weld integrity of the pipe is inviolate. After hydrostatic testing, a demanding regimen of non-destructive tests is undertaken to further ensure the integrity of pipe weld and pipe body. An ultrasonic shear wave inspection of the full length of the weld zone and the heat-affected zone is made. This is done in order to determine if there are any longitudinal and/or transverse discontinuities in the weld or heat-affected zone. The automated ultrasonic system includes fully automated guidance of each pipe, along with laser tracking of the weld seam to ensure precise positioning of the ultrasonic transducers relative to the weld seam. In addition to an analog display of received signals, the equipment includes an automatic audible, visual, and spray marking alarm system, which would be activated should a signal above the calibrated reference standard reflectors be received. Any potential discontinuity found by the automated ultrasonic equipment is manually evaluated with a handheld phased array shear wave ultrasonic machine in order to characterize the dimension and type of the discontinuity. The detailed manual evaluation of each discontinuity allows for a much more stringent automated ultrasonic regimen, as the machine can be intentionally tuned to more demanding parameters than the applicable specifications requires in order to intentionally generate a number of false positive indications. This provides confidence that the customer specification is met or exceeded for each ultrasonic test. In addition, the superior quality of the phased array unit, as opposed to the industry standard of fixed angle transducers, provides for superior pipe quality in that it allows a much more detailed characterization of each finding. This allows for a more finely tuned welding process as more detailed feedback is cataloged and ensures that even the most minute indication can be detected and eliminated as required. Calibration verification of the automated ultrasonic system is made in both dynamic and static conditions. The dynamic calibration verification is made at normal manufacturing speeds and is conducted multiple times per shift. In addition, static calibration of the handheld phased array units is conducted at least once per shift. Both dynamic and static calibration processes use precisely manufactured artificial reflectors to ensure that calibrations meet or exceed customer and other applicable specifications. After ultrasonic evaluation is complete, pipe ends are inspected by X-ray in a separate operation. The ultrasonic and X-ray operations are staffed by a Level 2 UT and X-ray operators, respectively. The Level 2 operators are supervised by Level 3 certified UT and X-ray supervisors. A separate real-time radiographic station is in place to X-ray weld repairs, provide data for statistical process control of the submerged arc welding, and to provide for any customer specification requirements that might require full-length X-ray examination of the weld seam. Any pipe that undergoes weld repair and subsequently passes X-ray examination re-enters the final testing process and is retested at both the hydrostatic testing station and the automated ultrasonic station to the full standards of the applicable specifications. Each pipe end is beveled to the specified profile, bevel angle 30 to 35 degrees, and root face of 1/16 of an inch plus or minus 1/32 of an inch. In addition to visual inspection of the ID and OD of the pipe's dimensional attributes are inspected to assure compliance with our customers' requirements. This ID following beveling process provides the profile and consistency that is so critical for reliable field-end matchup. After the pipe has passed all of the non-destructive testing, proving that it meets all applicable specifications, the pipe is measured longitudinally and the pipe length and identity become part of STUP's traceability database. Each unit of pipe carries with it a pipe number, steel heat number, the pipe length, and weight. This information is available electronically and can be physically viewed on the pipe. Barcode labels with both conventional 3 of 9 as well as two-dimensional PDF 417 barcodes are attached to each pipe. The conventional barcode consists of the traceable pipe ID number. The two-dimensional barcode is in addition to the paint markings and can be removed upon request of the customer. The latest radio frequency handheld equipment and effectively located wireless access points are incorporated to form a seamless real-time information support system. This allows for pipe tracking from COIL utilized through production and yard movement as well as coding and shipping.